So welcome everyone. It is my pleasure to welcome you at the Turing Fellow presentations. So the first, we have two speakers this time, and the first speaker is Richard Allmendinger, who is a senior lecturer in decision sciences at the Decision and Cognitive Sciences in Manchester Business School, who would be talking about experimental challenges in expensive optimization.
Okay. Hello, everyone. As Sophia said, I'm Richard Allmendinger and I'm based in AMBS. So today I'm going to talk about things I've been working on since my PhD, and these are topics I'm still working on and actually work even more than 10 years ago on them. So here's an overview of some of the projects I'm working on, but today I'm just going to focus on these four highlighted in purple. Probably I will only manage to go through 3 of them. But they have something in common, these 4 topics highlighted in purple. They all relate to expensive optimization. Expensive in the sense that evaluating a solution is costly, time-consuming, and or resource-intense. So rather than focusing on one of these challenges and giving you a deep dive with loads of different methods and so on, I'm giving you an overview of probably 3 of them, depending on time. And hopefully that will give you a good idea of the sort of stuff I'm working on. And if that's of interest, I would be more than happy for you guys to reach out to me. So these companies in the background here, they indicate, these logos indicate company involvement. For example, in one of the projects, I have a PhD project with IBM. I'm going to talk a bit about this and so on. Okay, that's the agenda. I'm going to give a brief introduction to expensive optimization. And I'm going to touch on Bayesian optimization because that's the method of choice we tend to use in expensive optimization. And then I'm giving an overview of these different resourcing issues. Probably I won't make it to discuss safety constraints. And then there will be questions at the end. So that's the setting we often find ourselves in expensive optimization. We have here a computer, and the computer has an optimization algorithm. The optimization algorithms tells a decision maker or some experimental platform what solution to evaluate next. So let's call our solution X. And then the evaluation itself is then, as I mentioned before, time-consuming, costly, or resource-intense. So that could be, for example, simulating the aerodynamics of a car or tasting coffee if your problem is to optimize the taste of coffee and come up with new coffee. It could also be chocolate or any other type of food or drinks. Another application, which is something we do a lot in Manchester, is actually drug discovery. So we can have an optimization algorithm that tells the decision makers which drugs to mix together in order to come up with a better drug. But also in tuning of machine learning algorithms, for example, hyperparameter tuning, you see that these experiments can be very time consuming. So all of them have in common that they take long or cost a lot of time or are resource intense. And once we have done an evaluation, they tend to be often noisy. The objective function value or the quality of that experiment is then returned back to the computer, to our optimizer, and then the optimizer tells us what is the next solution or candidate solution we want to evaluate. And that loop we would be doing this loop until we would be running out of time, money, or resources. So it's a standard, here's a formal definition of a classical optimization problem, but here we're looking at F. So F is time consuming or costly or resource intense to evaluate. Okay, and a couple of considerations we make in experimental optimization. Typically, because it is costly to do an evaluation, we want to do as few evaluations as possible. So we want an optimizer that converges relatively fast to a good solution. And Bayesian optimization is an approach that allows us to do that, but also people have looked at evolutionary algorithms, de-randomized versions of evolutionary algorithms, because classical evolutionary algorithms tend to require a lot of evaluations, which isn't great if you're dealing with expensive problems. We also want to have results that are reproducible, because think about the drug discovery problem. At the end, if the goal is to come up with a new combination of drugs, then you want to be sure that that combination of drugs, every time you produce it, its potency or side effects are very similar. Yeah, there shouldn't be much variation. So we want to have reliability as well in our optimizer. And then also robustness is quite important. So for example, if the optimizer tells us this is the optimal drug combination, then we want to be sure that we can actually manufacture this drug combination at scale. Yeah, if that's not possible because of whatever reasons, then that wouldn't be a good drug combination. Yeah? And then often we have a reference solution that we also call it a pilot sometimes. Yeah. A control sample that tells us whether we have underlying issue in our platform or not. Yeah, and then we would often compare the optimized solutions to a control sample. Yeah, so that's just to make sure that there are no underlying issues in the experimental platform that we use to evaluate solutions. So often the method of choice in expensive optimization is Bayesian optimization. At the high level, it's a sequential design method, and there are two main components that need to be decided on when you're working with Bayesian optimization. It's the statistical inference method, and then it's the acquisition function. So in Bayesian optimization, we start off with a random set of points. They may not be random. You may want to generate them using something like a Latin hypercube design. Once you have these points, you would apply a statistical inference method to it, and it's quite common to use a GP for that. And the beauty about GPs is that the GP can tell you what's the expected performance of a point you haven't seen before, and also what's the uncertainty in that expected point. Yeah, so here these sausages essentially indicate uncertainty. Yeah? So in both of these aspects, the mean and the uncertainty, can then be accounted for in the acquisition function, which is then here highlighted in green. And then the acquisition function itself, which is, for example, expected improvement, is very cheap to evaluate. So you can evaluate that function many times, and a solution that's doing really good on the acquisition function is then actually evaluated in real world. So only the one that you select here is then evaluated in real world, and only then you actually incur costs or time or resources. Yeah? And this loop is then once you have a new point evaluated, you again apply Gaussian process regression similar to here. Now you have 3 points rather than 2, and you keep updating your posterior. So this way, the algorithm, you would encourage exploration as well as exploitation. And Bayesian optimization has been extended in recent years to loads of different challenges. For example, now you can evaluate multiple solutions in a batch, because initially it was one solution at a time. Bayesian optimization has been extended to deal with constraints, different types of variables, not only continuous variables, but also binary, integer variables, or indeed a mixed type of variables, and also to multiple objectives. So has been proven as the method of choice for expensive problems. So, and a lot of the work I'm going to do at the Turing, or would like to do at the Turing, is making Bayesian optimization work for these challenges. Yeah. So now I'm telling you a bit about these challenges. Yeah. So change of variables during search is the first challenge, and that's a real challenge that I've come across with my PhD supervisor back then in 2012. When I was doing my PhD in Manchester, we were working with the MIB, and it was a drug discovery problem. So we were given a library of drugs, 30 drugs, and the algorithm had to tell the optimizer which drugs to put together in a cocktail and mix together, essentially. Yeah? We knew each of these drugs is potent, but we were hoping that putting 2 potent drugs together, 2 or more potent drugs together, that will lead to even more potent drugs. Yeah? So at the end of the day, we wanted to have very potent drug cocktails. We wanted to have cocktails that have no side effects, and we wanted to have cocktails that are cheap to manufacture. And well, what happened, and that's an expensive optimization problem. Yeah? So every combination required us actually to mix the drugs itself, and then try out the drugs on a sample, on an infected sample, and then measure its potency. So that's quite time-consuming and resource-intense optimization. And halfway through the optimization, the biologist told us, look, whenever these two drugs are in a cocktail, then the potency is very low and the side effects are very high. So we want to remove these 2 drugs from the library. And they may want to replace them with 2 new drugs, or they may just want to replace these 2 drugs. So that changes your optimization problem during the optimization. Yeah? So here I have an example. Imagine you have a drug library of 5 drugs, 1, 2, 3, 4, 5, and 0, and 1 means include the drug, include this drug, drug 1, and drug 3 in a cocktail and mix them. And the 0 means don't include the drug associated with that variable. Yeah? So and then here, let's say drug C and E, these 2 would be replaced. Yeah, so that's what we end up. So suddenly we do not care about any drug cocktails that used any of the 2 drugs, or indeed both. So here we were changing what we call the search space. And we would tell the optimizer, we have now changed the search space, we have taken away these 2 drugs, and instead we've put in this new drug into the mix. Yeah? That is different from classical dynamic optimization problems, where the objective function is just changing over time, but the search space itself remains constant. So here's more a graphical visualization of what's happening if you're changing drugs. So this is the standard scenario where we do not change any drugs during optimization. So your search space X at time step 0 remains constant. So even at any time step G, XG is the same as X0. Yeah? So that's a constant static search space. And that's normally what we have in an optimization problem. Then there's the other extreme where the biologist says, I want to replace my whole library, drug library, with new drugs. And that would look like this. Yeah. So your current search space is completely useless, essentially. And then you have to essentially restart the optimization to start scanning through that space. But where we find itself in this scenario, where only some of the drugs are being removed and potentially new drugs are being added, but there is a good chunk in the search space that remains the same. Yeah? So the question in this problem here was, how can we explore this new space as efficiently as possible while also keep searching for this space? Yeah? Because this space down here is not available to the optimizer anymore, so we don't need to search for this anymore. Yeah. So we have developed this simple method for mutation that is doing exactly that. It keeps optimizing these ones, but it dedicates us a fixed number of evaluations to that space to ensure we explore that space. Yeah, and we published that method that it has indeed been used to drive the optimizer for more efficient drug cocktails. And that was a good piece of work that we actually published in Nature Chemical Biology, 2011. So back then we used evolutionary algorithms. So these are population-based random search heuristics. But these days we would really use a Bayesian optimizer to tackle the same problem. So in future work, and the work I wanted to really at the Turing Institute is to explore the application of Bayesian optimization to this problem. And it may require also the combination of Bayesian optimization with transfer learning or other machine learning techniques that are around. And the application we looked at here was drug discovery, but I'm sure there are other applications where the search space changes over time, and it would be good to understand what are these applications. So if there's anyone in the audience here who has a similar application or thinks they have an application where variables change over time, you should really let me know. Okay, I'm moving on to a different challenge now, objectives with different evaluation time. So this is a multi-objective problem, similar to the drug discovery problem. Multi-objective means you have more than one metric to optimize. The classical example is, imagine you want to buy a car and you want to have a car that's cheap, but also and also comfortable. Yeah. But typically these two criteria in conflict. So you have down here, you have a car that's very cheap, but not as comfortable. Up here, you have a very expensive car, but that's comfortable. So that's a Lamborghini. Not sure it's more comfortable than this one. So if that would be a Bentley or Rolls-Royce, that would probably make more sense, but I think you get the idea. And then there are loads of these trade-off solutions that give you all possible combinations. So all optimal possible combinations between comfort and cost. So there's no reason to believe that these two objectives are the same. They can vary in their complexity, in the level of uncertainty, and also in the time it takes to evaluate them. So we call them, they can be heterogeneous in a sense. Yeah? So we looked at the scenario where you have some objectives that are really fast to evaluate. For example, the cost of manufacturing a drug. That's in essence, in very simple terms, summing up the ingredients, and then you have the cost of manufacturing a drug. And that's very fast to do. And then you have the slow objectives. So evaluating the potency of a drug. As I mentioned before, you actually have to mix the drug and then try it out on an infected sample and so on. That can take a lot of time. Or these CFD simulations, they can take a lot of time as well. So we have a mix of fast objectives and slow objectives. Yeah. And how do we deal with these, with a problem, multi-objective problem that has fast and slow objectives, but there's also a time budget. Yeah. For example, you may need to arrive at an optimal solution in the next 2 weeks. Yeah, so that changes the game a lot. So the time budget. And we looked at this scenario for the first time, it was 2013. And in fact, we were the first people who looked at this scenario, and that has now led to a number of research groups looking also at heterogeneous objectives, which is quite great. So a naive optimizer would do the following. So imagine X1 is one solution or a set of solutions that are submitted for evaluation on the fast objective and slow objective. And if the fast objective takes this much of time and the slow objective of this amount of time, a standard optimizer would wait until both objectives have been evaluated, and only then it would generate the next solution and so on. But you can see, I mean, and we call this strategy waiting. You can see there's a lot of time objective function 1 is idle, so we're not making use of that. Yeah, which isn't maybe great if you need to deliver an optimal solution within a given time period. Then there is another alternative, fast first, where we would evaluate the fast objective as often as we can, and then just make sure at the very end that at least some of the solutions are evaluated on both objectives. And then there's a more intelligent way, what we call an interleaving strategy. So we would, instead of waiting here for the slow objective to finish, we would evaluate different solutions on the fast objectives, and we could maybe use them as look-aheads to decide which solutions evaluate here on the slow objective. And these strategies, the interleaving strategies, can become really complicated. And here we have made use of transfer learning, for example, to decide which solution should be evaluated here and here to the slow and the fast objectives. And we found out, the optimization performance is affected by the difference in evaluation time. Is the slow objective much slower than the fast objective, or is it only a bit, by the correlation between objectives and so on. And future work, again, that I would like to do to Turing would be explore other machine learning methods in combination with Bayesian optimization to deal with this problem. And there's work on multi-objective optimizers that account for correlation. For example, Shah and Garamani looked at 2016 at the problem, but they haven't looked at how to account for different evaluation times. They just considered how can we account correlations to drive search, and they've shown that's actually can be quite good in terms of search performance. So I would be keen to extend that method to deal with different evaluation times. And also, no one so far looked at more than 2 objectives. So all the research so far looked at 1 fast objective and 1 slow. But what happens if you have, let's say, 10 objectives and they vary quite widely in the amount of time they need to be evaluated? So there's a lot to do. Now, the last challenge I want to tell you is ephemeral resource constraint. So to do a physical experiment, let's say mixing cocktails of drugs, you actually need to have the drugs available. You also need to have maybe equipment available to do the mixing. Yeah. So it's not only raw materials you need equipment. You maybe need a skilled engineer who is doing the mixing, if it's not done on a machine. Or in a CFD simulation, you may need to have a license available to actually run the CFD simulation. So resources may not be available temporarily, for whatever reasons. The engineer might be out of office. You might not have storage for any new raw materials. The delivery of raw materials may be delayed, or an instrument just breaks down. So yeah, how do you account for these temporary non-availabilities during search? And we use the concept of what we call ephemeral resource constraint to model availability of resources. Again, that's our classical problem, and we have added the notion of time, and here T, but also the notion of this E, which means evaluable search space. So we say a solution can only be evaluated if it's within ET, which is a subset of X, and ET represents the set of solutions we can evaluate at the current time step T, because we do have the resources available to carry out these evaluations. And as you can imagine, resources come in different shapes and forms, and therefore they can be non-available for various reasons. So we defined various types of ephemeral resource constraints, and quite a few of them are actually real constraints that we have seen in the work we've done at the MIB in Manchester. And the way we simulate these constraints is through a function, if-else function, rather than an equation, as we would use for standard constraints. So we come up periodic constraints that would simulate scenario where a skilled engineer is available only on one of the days of the week. Your commitment constraints, because there could be experiments where the instrument, once you specify certain settings, you can only change them the next day because it requires the instrument to be washed and cleaned, and that's only done at night. So you're committing to a certain instrument setting. Then random constraints that model, for example, breakdown of a machine. And then we looked also at more complicated constraints where an algorithm had to decide which resources to buy, when to buy them, when they arrive, and which storage space to put them, and so on. So these constraints can become arbitrarily complex. And there are various questions one need to arise when dealing with these constraints. Who is in control of resource availability? Is it the algorithm or is it the human who is making decisions on which resources to order and where to put them once they arrive, and so on? And we looked at different ways of dealing with these constraints, from classical methods like just wait until you have all resources available and then continue with your evaluation, or force a solution into this ET. For example, if that's the solution your optimizer wants to evaluate, you may want to force it in that space, in order not to wait. And we came up with loads of other strategies, and they all performed quite well. But we also looked at, can we learn to switch between these static strategies during an optimization run? And we used that using reinforcement learning as well as multi-arm bandits. We also did a bit of theory on deciding how to set parameters of an evolutionary algorithm when faced with a particular type of ephemeral resource constraint. And this is work I'm now extending with IBM in form of an iCase PhD studentship. Okay, how do I do on time? Okay, I think I have 20 minutes almost done. So I'm not going to talk. Yeah, I will finish now. I'm not going to talk about safety constraints, but I have slides at the end if anyone is interested. So that's my last slide. So I hope it came across that there are different types of resourcing challenges that an optimizer may face. And the challenges I showed you today, these were challenges we actually have faced in real physical work with biologists. And they haven't actually been considered or defined in the literature before. So we were the first to experience them and then define them and publish them, which is quite cool. But our understanding is still limited about each of these challenges, and more work needs to be done. In particular, if new people want to enter, for example, if new academics or industrialists want to look at these challenges, we need to make it as easy as possible for them. And therefore, we need benchmark guidelines as well as software to reduce that barrier of getting new people into these fields. And I hope it became clear that it's not just extending optimization that we need to do. We need to combine optimization potentially with scheduling, with machine learning methods, with control methods, and uncertainty handling methods, and so on. So it can become really complicated if you want to deal really well with these constraints. And yeah, finally, it would be good to validate these methods more on real-world problems. And so far, no one looked at combining these challenges in one. So people looked at these challenges independently from each other, but what happens if we have a problem with 2 or 3 of these challenges in one go? That is it from me.
Thank you very much. We have 2 minutes for questions. Any questions?
Hello, my name is Graham Phillips and I'm from the BBC, Research and Development. Have you, you only highlighted a bit of your work there, and I was wondering if you've looked at situations where conducting the experiment changes the search space. So I'm kind of thinking about commissioning TV shows as being very expensive experiments, but once you've made one show, you can't like make the same show next year.
Okay, so you're talking about it's like a stage-wise. I mean, it is like a commitment constraint, yeah? It's like you're committing initially to a certain decision, and then that opens up certain other decisions, yeah? Is what we call a multi-stage optimization process, similar to that, yeah? It sounds like. We haven't looked at this, but it is something we have started to look in the context also of biopharmaceutical manufacture. So, and people also refer to this sometimes as bi-level optimization. So it's an interesting problem, yes. But so far, everything I told you today was single stage, not multi-stage.
Okay, thank you.
But we should maybe catch up afterwards.
Okay.
Thank you.
So we have time for one more. Oh, yeah. You're muted.
Yeah, Richard, very exciting talk. You know, they are quite interested in this optimization involving in your side. Quite somehow slightly different from our side. But one of the questions you mentioned, clearly when you try to optimize something, there will be changes in the variables, right? But once the variables change, you know, how does that your new optimization, you based on new variable, how is that related to the previous work you have done? If you have already done some optimization with the old variable, now they put in new variable. My understanding from your talk is clearly they are linked, right? You're not really treat a complete new problem with a new variable, right?
Yeah.
Some part of the old knowledge probably migrate to that. How do you integrate that too?
It's a good question. It's a good question because what you don't want to do is you don't want to spend hours and hours on experimenting, and then if you change, let's look at the scenario, you just remove one drug or you add one drug, you don't want to restart the optimization. So there must be a way to reuse the information you've gathered so far in order to explore the new space more efficiently. There must be a way. What is the best way? We don't know. The method we came up with, essentially, we had to come up with during the optimization. The biologists told us without telling, they told us halfway through the optimization, look, we want to change this thing. And then we had to essentially 2 weeks to come up with a method. And that's the method we came up with 10 years ago. And that method was then used. And since then, I haven't looked at the problem. So one would expect something like transfer learning could maybe be used for this, or you can identify, let's say you replace two similar drugs, you would expect maybe that there's a correlation between two similar drugs. You know, you take one drug and then you put in a new one in that has similar properties. So maybe there's correlation, and then what worked well before maybe works well even now with the new drugs, but you would have to try it out experimentally, yes.
So there isn't a kind of methodology to deal with this, right? Or there is
no methodology. The naive methodology is just we start from scratch if we change.
Yeah, I think we start from scratch is basically waste what you have done in the previously, right? I think that's probably yeah.
Okay, thanks very much for the interesting. I had some questions, but I can email you later because no time.
Thank you.
So thanks for the very interesting talk. And our next speaker is Zhantao Ding, who is Professor of Control Systems, the Department of Electrical and Electronic Engineering, who is going to talk about distributed algorithms for network-based optimization and machine learning.
The talk is already said is optimization and machine learning. But my background is actually control engineering. I only moved to this area in the probably last 5 or 6 years. The motivation behind, for me, is probably more or less from the control perspective, as you will see later on. So the talk is basically probably 10 years ago, a little bit more than 10 years ago, I looked at the network-based control, consensus control, etc., as something like a multi-agent systems. I will have a quick covering about the background there, and then from that sort of a consensus or network-based approach, then I moved to look at the optimization algorithms, and then look at say how can we do kind of a distributed learning main idea for all this kind of work is say, okay, if we are doing something in a distributed manner, what can we do? But more or less from a control perspective. So the motivation is actually quite often, you know, we are dealing with. This is a problem I worked probably some time ago. Look at the formation control, right? We do have a multi-agent with different robots or even UAVs, etc. Try to coordinate their motion. So through the network, or they even involve robotics, or those automation of the cars. And then, you know, I'm within the Department of Electrical and Electronic Engineering. We have many colleagues look at the smart grid, sensor network, smart city, etc. The common phenomenon actually is it involves network. So my starting point to look at those network is actually we basically integrate the dynamics of the individual dynamics with the network. So the mathematical tool for that is those graph theory, in particular the Laplacian matrix. So that one basically shows the connection between different agents. We use the adjacency matrix. And those Laplacian matrix plays an important role in how we decide how to determine to share the information, how to determine, say, when I was doing formation control or consensus control. Our control law actually to a large extent depends on the eigenvalues of Laplacian matrix, in particular the smallest non-zero eigenvalue, they call it network connectivity. That one basically determines how strong the agents are interconnected. Then when we move to the optimization or use a distributed optimization, that particular eigenvalue still plays a very important role, as we will see later on. So as I said, I started with the control. If you look at the control, it's pretty simple. If you want to do it, it's basically use a relative position, and then you see this is a if you look at a single integrator, I think many people in computer engineering, they don't bother to look at the detail of the dynamics. They simplify to this kind of a single integrator. Then the consensus control is pretty simple. By doing that, this is an Laplacian matrix, right? Then you can get all the variables will converge to the common value. Doesn't matter how the individual states are. And then if you want to design something which you say basically you get the input and then you get a common value as output, then something like for those control guys will do the PI control, say integral control, some kind of integral action to move it to the average value, because otherwise from the control theory point of view, you know, naturally everything, once you apply control to achieve stability, variable converge to zero. If you don't want to converge to zero, then you have to put some integral actions. Related to optimization later on, you know, the optimization value surely is usually non-zero. So this kind of interaction does appear. We mentioned this one, the consensus control. Okay, I think we need to move to the optimization. So optimization, thanks to the introduction of Richard talked about auto optimization, right? So the sense of what I'm trying to show here is basically we do optimization in a distributed way. Suppose we got we try to formulate the problem into not the one machine or one agent try to solve it. We need the multi-agents to solve the optimization problem. So what do we do is if we want to minimize optimization function with one variable here, what we do is actually we can put that into a summation of a number of functions, and then the variables, because in each agent they may have its own variable, but if those variables are at the end to be converged to the same value, or if the mechanism, there is a mechanism to ensure that they will agree to the same value, then these two problems will be equivalent. That is the principle how we do the distributed optimization. And of course, this is unconstrained. Then if you do with the constraint, then we can more or less do the same thing. The basic idea about achieving this, once you have done the distributed one, it's more or less the same as what we do with the individual agent. What you can see basically, for example, if you use a gradient method, right? Then this part is the same for individual system, but because it's through the distributed manner, then there will be something involved with the network communication, and there will be something also with the integral action, which I mentioned earlier, so that it will converge to the right place. So if the algorithm is properly designed, then we can show, in fact, it converges to the optimal value. So what we are doing here, basically, we are designing a multi-agent dynamic system, and the converging point is the optimal solution. So if you look at the constraint, which is I will come back to that for the application, is a resource allocation problem. One of the issues actually I applied later on is actually to look at, for example, the frequency control, node frequency control for power systems, right? Basically, we need to achieve node and generation balance. So this kind of constraint, with this kind of constraint, then the consensus value there, because here, if the unconstrained, then each variable at the end will converge to a common value. With the constraint problem slightly different, the convergent value is not the solution itself, it's actually the Lagrange multiplier. So Lagrange multiplier, if that converges to the common value, then we can guarantee the optimal solution. The solution here, if you have the optimization, if you have objective function, yes, that's what you can do. Based on this, we have tried in the probably 3 or 5 years ago. We tried different algorithms with various network topology and also sometimes various conditions of the objective functions. But we also recently explored the situation if we do not have a clear objective function. How can we approach this optimization problem? One way is basically we can use those kind of surrogate. Based on the data, we can do the surrogate optimization, and we can also make it to the distributed manner. You might wonder, say, what is the advantage by using the surrogate? What you can do, people can argue, say, we can offline learn, or we can offline curve fitting, etc. We can get optimization function, and then based on the optimization function, then we design our optimizing algorithm. Of course, you can do it that way, but actually there's an advantage to put the two things together. Because of time, I probably look at this schematic diagram here. Say, if you look at optimization problem, if you do the curve fitting, basically, what can you do? The criteria could be the minimum error, right? You will try to minimize the curve fitting errors. But actually, you don't have to be good at all the places. You only have to be good around the particular solution, right? Around the optimal solution. So by combining these two methods together, yes, there's an advantage. Okay, instead of fitting the curve separately, we do the more or less curve fitting together with optimization. By doing it together, then we only need a good approximation around the solution. Of course, when you do it, because we are dealing with basically curve fitting, some kind of learning involved, and then we're doing optimization. It's basically we use a projection algorithm because we are searching the optimality within some intervals. You need to guarantee that we are searching enough space and it doesn't converge locally. So there are certain things we need to take care in the design so that it can be this kind of convergence can be guaranteed. So this is one of the recent results we looked at. So I think let's move to the machine learning side. So one of the things actually in the machine learning, to be honest, my understanding of machine learning is more or less from a kind of optimization point of view. I think when we learn something, for example, many people spend a lot of time trying to learn a particular function. There are some optimality issues within learning. And one possible problem is actually learning algorithm you could converge prematurely, right? It's something like you converge to local minimum. So how to avoid that? Also, the multi-agent system can be useful, basically by involving more agents to learn something together. then that could prevent, to a certain extent, the premature converging to local solutions. So the intuitively, I was thinking that okay, if you got a 3 machine to learn 1 hour, probably better than 1 machine to learn 3 hours. So during the learning, either deep learning or the reinforcement learning, we tried both. So if they are exchanging information about the different agents, can we achieve better results? In fact, the answer is actually, the answer is true. Of course, now the people talk about federal learning and talk about the protection of privacy, etc. Right? I think one of the things that if you learn like a federal one or distributed one, you don't have to get all the data together, right? You can exchange other information rather than the raw data. And hopefully, just as what I showed earlier, hopefully just as we can achieve global optimization using distributed manner, and we can achieve probably even better learning outcome than individual learning, then put all the data together, right? So that's the main idea. So I have a schematic diagram here, try to show. So, okay, we got a single machine learning, right? You got a parallel computing something. So the distributed is basically, we are learning individually, then we sharing the information, right? Share the information. Of course, you could have federal learning. It's not only distributed, you also got some coordination at the top, just like in the control field. For those who are familiar with those hierarchical control, I would have thought the federal learning more like a hierarchical control. You got some sort of structure there are coordination among them. But distributed learning, just like distributed control, we don't have a central authority, right? There isn't a central unit, but more or less through the peer-to-peer communication, then you can still achieve good learning results. Okay, so of course we can have some theoretical analysis to guarantee the convergence, right, in some way, and then based on that we try say, okay, this is actually a simple example. We do the learning individually, we share the weights, and then we use a standard test data set to see whether we get good results or not. In fact, the initial trial didn't show a big improvement. Then I thought maybe the data set we tried too simple. Probably that was true. And then we tried a different data set. Then yes, we have this kind of a clear improvement over individual learning. Okay, this is a result probably a couple of years ago. And then we also look at it and say, okay, how to share this kind of results, right? And if you share the results, how to determine this sort of learning rate. So we did some further investigation, try to give a guideline on the learning rate, and within certain learning rate, so the actual distributed learning will converge. So this is a result just appeared last year recently. Okay, we also tried different ways of try to make it adaptive in a way, but we have to be careful actually here. If you award those learning better one, you could actually end with a premature convergence, right? So there is a kind of careful play between the two. Okay, so plenty of things to try, but of course this is only just a theoretical guideline, and in actual applications we have to be careful. So we tried also some switching the graph and data compression with the sharing. To be honest, when we share the data, you don't have to doing the exchange information. You don't have to exchange everything, right? You only have to exchange a certain part of it. You can still achieve good results, because we all know that in the learning, in the deep learning, those are ways, there are huge redundancies there, right? So you don't have to share everything. Okay, so those probably learning over the network. We tried also for the compressions, etc. Okay, recently we also tried those kind of game network, basically. For example, image processing, how to create a fake image, right, to test the identifier. So we got a discriminator, we got a generator. It's something like a game. We can play in both the games and make sure that the generator keep improving and the discriminator also keep improving. And And this kind of things, I think I can just show the results. So those are the final data sets we tried. We just use the handwriting to see what are the generator try to generate something which is difficult to differentiate, and the differentiator will try to improve, make sure they can differentiate. So those are the something which we have done recently. Okay, we did try some applications to the smart grid and also to the learning. One of the things that actually we tried is a deep breathing network to the short-term node forecasting. Basically, what do you say? We have this. We have the distributed learning, and then we can say that actually we apply at least better than some of the single learnings. So the multi-learning, distributed learning, yes, it works. We also tried with the reinforcement learning for the we also tried the reinforcement learning for the for those day ahead bidding for the those electrical price, etc. So the results also looks quite good. So the overall the talk is basically tried here, as I said, I'm a control engineer through the consensus control, actually getting involved with the network, and then we try to apply some sort of network communication ideas to the learning and to the optimization, and then we tried also something to apply to the electrical power system, mainly the optimization, which I haven't shown the details here, and also even learning, try to predict the node or predict the bidding for the next day, etc. We get some reasonable good results. Okay, those are talk actually based on those recent papers, mainly of my students in the last 2 or 3 years working on those topics. Okay, those students are actually they also with a control background or the electrical engineering background, but they none of them with a computer engineering or the optimization background. So that there is a strong flavor. We try to apply control technology to this kind of problems. But it's I think my talk finished here. I would be happy to take the questions. Yeah.
Thank you very much for your talk. Do you have any questions? Anyone to ask questions? Yeah.
Yeah. Hi, Richard. Yes.
I've got a question. So the agents, I think I missed this. The agents, they're trying to solve the same problem. Yeah, they have the same capabilities. They follow the same objectives and so on. They are homogeneous. Yeah?
The objectives can be different. As I mentioned, okay, if I go to that one. Sorry, I have to share again. Okay, if look at here. So if you have the objective function, we can split that into number of functions. Each agent has only to take care of his part of it. But there is a common consensus on the value, because initially that is only optimization with respect to the f without any constraint. Then by doing that, we introduce extra constraint. So each x here must converge to the same value. Then these two problems will be equivalent. So basically, unconstrained problem, when we put in the distributed manner, it becomes a constraint optimization problem. That constraint condition is the consensus condition. That's for the unconstrained. If say, for example, for this one, the resource allocation, then again, each agent got its own objectives to look at, and then the subject to this kind of constraint. But in this case, the mechanism behind is to make sure that the Lagrange modifier is converged. If Lagrange multiplier converges, then it means this global constraint will be satisfied.
Okay.
So basically, each agent you have a freedom to design what kind of optimization function they are looking at.
Yeah.
Do you have any other questions?
Hello, yes.
Yeah. Please go ahead.
Yeah, I was just wondering, do you have any more sort of information on the federated learning side?
Federated learning, to be honest, I'm not an expert on that. Although one of my students is working on that, we try to apply to the power system issues. I worked on the distributed learning for quite a few years. And until recently, then I saw the federated learning is quite hot. But intuitively, I believe that the federated learning probably I think federated learning, if you can coordinate it better, surely it's an advantage, right? Because from the distributed learning is more simplistic. Say we only treat each of them more or less as a peers. But if there is a coordinate, I would think they can do something better, definitely. But so far, I haven't got really, my team haven't really got the fantastic results yet. We are more or less trying to apply federated learning to some of the power system problems at the moment.
Okay, yeah, I was just wondering, yeah, how you would go about coordinating the sort of hierarchical levels there. Yeah,
I think the coordination, it is important, right? You have to determine what sort of things you coordinate, what sort of things you need the individual agents to learn, and how to distribute those kind of tasks, I think. I'm not sure whether there will be any general guidelines on that, you know, but it would be interesting to see.
Yeah, it sounds like trial and error essentially at the moment.
Yeah, it's true, probably. Yeah.
Okay, yeah. Okay, thank you.
Thank you. Any more questions? Okay, we have 2 minutes left.
Okay, I will ask one more. On the agents, I mean, do you have a scenario where the agents are heterogeneous? Like we have in the business school, we look at the scenario where agents are companies. So they compete, but they can also cooperate. And some agents have special powers, you know, like big companies, they can change the optimization environment for other agents, the SMEs, let's say, you know, they set kind of rules, and therefore that may cause a change in the search, in the search space or in the objective function. I don't know if you have something.
Yeah. I think Richard, that's something interesting, which I haven't talked here. Yes, I actually have worked on some of the issues. Probably to model that problem is more like those generalized natural equilibrium. Basically, each company got its own objectives, and then there's some sort of global constraint. And then each company will try its best, right, to make sure his objective is optimized. Slightly different, I think, from the distributed polarization we've been looking at, is perhaps more put in the category like sort of generalized natural equilibrium.
Yeah, maybe.
Yeah, because they're not homogeneous, and each of them got their objectives to maximize or minimize, and then there are some interconnected constraints, right? And then at the end, if they play freely, how can they end with the equilibrium? So if you're interested, actually, I can share some of the results in that aspect, but I haven't talked here.
Yeah, thank you.
Okay, this is all the time we have for today's talks. I'd like to thank both speakers for a very interesting discussion. And the talks have been recorded if you want to access them. And thank you again. Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.